start. Let's do just this one fun thing. I'll do this backwards. Normally, I introduce the numerical technique, and then we talk about an antenna type that we use for this numerical technique. Instead, I will jump right into the antenna, do a little show and tell, and we'll talk about the numerical technique on Wednesday. Is that okay? So here's our topic, mini topic for the rest of the lecture. The Yagi-Uda Array. This is a wire antenna, not unlike a dipolar, but it's a little bit more complicated. And it was discovered by some Japanese researchers about 100 years ago. Yagi was the advisor. Uda was the Japanese grad student that probably did all the work. So it's called the Yagi-Uda Array by people that know a lot about antenna history. But just RF engineers in general just call it the Yagi. The Yagi-Uda Array is kind of complicated. Just call it Yagi. Oh, give me that Yagi antenna. So once again, the graduate student, the poor student that does all the work, or engineer that was in the trenches, in the drudgery, shafted from the credit. Well, what is the Yagi-Uda Array? Let's go ahead and start with a dipole. You make a half-wave dipole, so they should have an omnidirectional pattern. In azimuth, this is the Z. You're going to have your typical approximately half pump of sinusoidal current flowing up, down synchronously along here in a standing wave. And then what Yagi and Uda decided, they wanted to make a directional antenna that was very simple. You could make it out of wires. It had really good front-to-back ratio. That's a parameter that comes up a lot in antenna engineering that we haven't talked about in the class very much, front-to-back ratio. That just means that what is the difference, usually in dB, they do it in a linear scale, front-to-back ratio is usually reported as a ratio of gains, front gain to back gain. But almost always it's reported in dB. So it's really gain in dBi in the desired direction minus gain in dBi in the backwards direction. And it's very important to have good front-to-back ratio in some scenarios. That's often what cell sectors are really interested in. Yeah, they want gain in this direction where they're serving their customers. But they're also, the cellular engineers are smart. They know that they're operating in an interference-limited, not a noise-limited environment. So they're much more interested in some ways with rejecting any of the people that are using those same frequencies behind the sector here. So they want good front-to-back ratio. That's something that they're very interested in. Oh, Jim.
What is a good front-to-back ratio?
What is a good front-to-back? Infinity. Perfect. It's possible to make that type of antenna. You put a null in the back. Two dipoles that are 90 degrees apart at quarter wavelength in space. Quarter wavelength, and then fed 90 degrees out of phase. But one is constructively interfering in one direction, and one is negatively interfering in the other direction. You make, in theory, an infinite front-to-back ratio. Now, in practice, nothing is ever infinite. So sometimes you have to live with, the simple front-to-back ratio of a Yagi-Uda array. And what Yagi and Uda decided when they started experimenting with this thing is that you can add something called a parasitic element. It doesn't even have to be electrically connected. And what they did, they called their dipole, which was electrically connected to a source, they called that the driver. And this bar that was a little bit bigger, maybe like 5 to 10% longer than a half-wave dipole, they put it anywhere from 1/10 to 1/4 of a wavelength, 0.1 to 0.2 lambda away. And they called this a reflector. because this is in the near field of this antenna will excite currents on here. That will be slightly different in phase because of the slightly larger length, and it basically acts like a reflector. It constructively interferes with the driver in this direction and destructively interferes in this direction. And there's really just a sinusoidal standing wave of current on this length that is at a slightly different phase and amplitude as this one. And so those are 2 degrees of freedom that you have to play with the Yagi. Exactly how far away do you get that reflector and how long? There's no one solution for a Yagi, it turns out. You can shorten the reflector and then change the distance and get it to work almost a little bit better than what you started out with. You can kind of tweak those 2 parameters. So there's a reflector. And that actually gave a really nice boost to the front to back ratio. You have a couple of dB gain of improvement in this direction and suppressed the back lobe by a couple of dB, depending on how you organize this thing. Then what Yagi and Uda discovered was you could put a slightly shorter element here, similarly a fraction of a wavelength, 0.1, 0.2 type of distance away, and that is called a director. And the director does the opposite of a reflector. It's phased in such a way that it draws in the wave in this direction and constructively interferes without even being electrically connected to here. This is all just capacitive coupling and inductive coupling between the elements. It's really interesting. And it also, in drawing the radiation in this direction, it suppresses by a few dB what's going on back here. And then the next thing Yagi and Uda discovered was that you could keep adding directors that's almost the same size, just a little bit less than a quarter wavelength. So all the directors are, this is a half wavelength. The directors are less than a half a wavelength. And the reflectors are usually greater than a half, slightly greater. If you kept adding directors, you could keep increasing the peak gain and the front to back ratio of this system. You make a really nice, simple directional antenna. So people around the turn of the century, shortly thereafter, really started to investigate the Yagi-Uda Array, tabulated all sorts of configurations and dimensions you could make Yagis. And anybody could take a bunch of wires and clip them together. And usually there's some sort of stabilizing bar here. You can make it even out of metal. It doesn't matter because it's cross-polar. Although a really good designer can make it out of PVC pipe or something plastic that's translucent to RF. You can even glue this down to a cardboard. My senior design project, my capstone design in my antennas class was making a 3-element Yagi, and we glued it down to cardboard. If you didn't have maker spaces back then, we had cardboard and glue and brass wires. That's all you need. Now, Yagi and Uda also said, what happens if you add extra directors? Nothing. Kind of makes sense, right? If this is already reflected in that direction, adding extra reflectors is not going to do that much because you've already reflected the signal quite a bit. However, because what you're really doing in this instance is almost making like a traveling wave, almost like a waveguide. This parasitically couples to this, parasitically couples to this, parasitically couples to this, and it draws the radiation in this direction and focuses the power, increasing the peak gain, decreasing the half power beam width. We have a question or a comment. Oh, yeah, Rehan.
So the difference between
Where it's placed and how big it is. Reflector is always a little bit bigger than a half wavelength. Directors are always a little bit smaller. If you start putting directors on this side, it's not going to do anything because there's a reflector in the way. If you put a reflector in the middle of this system, it's going to make the whole thing messed up. Yeah?
So they're both just wire.
That's right. Welcome to the messed up view of electromagnetics, the messed up world of electromagnetics. They're just pieces of metal hanging in space. And yet, so if they were connected to sources, we would call this an active array. It's still an array, but because those are not connected to sources, we call them parasitic elements. They don't have sources of their own. All the power that they draw is from coupling to eventually things that do have sources. And that's one of the things you have to get used to in antenna engineering. We're now getting to the point where we're studying electromagnetically more and more complicated systems. So you're going to see crazy things like this. Hunks of metal that are critical to the operation of an antenna, but aren't connected to anything. Are just using near-field coupling to accomplish what they need to accomplish. And this is also what is vexing about the Yagi-Uda Array, is that why you can't solve it on pen and paper like you could with our other wire antennas. Because we kind of know what the current distribution is going to be on these things. It's going to be like a sinusoidal hump, a little bit bigger, a little bit smaller. But we have no idea what the phase is going to be. How do I calculate the parasitic phase on these directors? The offset from here to here to here to here. Very difficult, and that's why we need to resort to the numerical methods, like the method of moments, to do that. Why this is a class 3, let's punt numerical antenna problem. Any other questions? Any questions from home? Oh.
Use the reflector directly.
Well, because if you make the reflector a little, or the reflector a little bit less, the phase that gets introduced into that parasitic element is more like the phase in the director, and it will start sucking the pattern this way. So the length, it's actually very intuitive in a way, right? Oh, it's bigger, so it's kind of like pushing the electromagnet. It's not pushing. Don't use those adjectives. Don't tell anyone that I taught you that. It's just a mechanical way to think about it, to remember what's going on. But really what's happening is that you're adjusting the length. Different lengths will introduce different phase offset from one standing current pattern to another on the parasitic. And that's what's actually doing all the work in your system. And that's also why changing around the positioning of these things and playing slight games with the length, even what looks to be relatively small changes, can lead to big phase offsets in the parasitic element. Question. You.
What is the separation difference
Between the directors? This is a little bit more loose. You can do like 0.1 or 0.2 lambda, although there are certain designs where you don't even have to make these uniform. And you might even go like a quarter wavelength or a third of a wavelength in some instances. What's interesting is that if you enforce uniformity, you will get one sort of design out of your Yagi. But if you start playing games where you like move these two closer together, and then this whole system maybe moves farther away from this, and you've got a lot of degrees of freedom here. And you can often optimize and get a slightly better Yagi by making a non-uniform series of directors. And you can imagine that you might even be able to, with hunting and pecking around in your NEC code that you'll be using on your next homework assignment, you might discover a really, really weird ratio of directors, sizes, and spacings that nobody's ever stumbled across and might actually perform pretty well. The reason is that winds up, if you have 10 directors, you wind up having spacing of 10 elements and then sizings of 10 elements as well. You got 20 degrees of freedom to work with. The chances are nobody's ever quite designed a Yagi just like you if you've got a lot of elements. Okay. Any questions?
Pretty bad.
Consistently smaller like the one in the lab. So if I remember, the one in the lab has a driver, one reflector that's a little bigger, and then these are all roughly the same size, but they're not exactly uniformly spaced. Is that true? Ah, I don't think the ones in the lab do, but there is a type of antenna that you may have seen either in the lab or where the things do get smaller. This is actually a very common type of antenna. How many have ever seen an antenna that looks like that? This could be a bar going through there, but you basically have what looks to be like collapsing dipoles to a point. That's called a log periodic antenna. This, unlike the Yagi-Uda array, you make a slight change in the geometry, and all of a sudden you get a very broadband version dipole with some directivity in this. It's not as directed as a Yagi-Uda array, but it's much broader bandwidth. And the reason is, what you've really done is you've taken a transmission line here, and you've attached to it various dipoles that, because they're successively smaller in a geometric sequence, that's what they call log periodic, when you dial in the lowest frequency of operation, you're exciting this dipole, and these other dipoles are so badly tuned that they don't even draw waves, current from your feed line. You have basically like, say, a 75 ohm feed line. This antenna resonates at low frequency. Everything else looks like some awful R sub rad plus some J sub huge, and it doesn't even draw power from that feed line. So everything kind of dumps into one element, and it radiates, has a good impedance, looks like it's matched. You dial up the frequency. As soon as this guy detunes, this one starts to tune, and you get a well-matched antenna. Then you dial up in frequency a little bit more. Now this one starts to tune, and this one detunes. What's more, you get some gain in this direction and some suppression in that direction, because it looks like you have a 3-element Yagi here, doesn't it? If you've designed this thing right, you kind of get a Yagi that has 3 elements and some inconsequential directors that are smaller than directors should be. So for the same size, you'll never get the gain that you get with the Yagi-Uda array, but you will get a lot of bandwidth if you tweak everything just right. Because it looks like you have a little 3-element Yagi with each successive increase in frequency up until you get to the smallest element. So you can make a very broadband antenna array like this. It's very simple to build. You can easily make something that has 10-to-1 bandwidth. How many have seen an antenna like this before? Where did you see it, Jeremy? On top of buildings, yeah. It used to be a great way to have VHF radio transmission. We lived in a very rural part of Maryland growing up, so we had something that was kind of like this, a couple stages of this up on top of our house, horizontally polarized. VHF is horizontally polarized. And then it was on a little turntable. You could dial in the different directions that it would point, go back and forth, point it towards Baltimore, get a station really badly with a lot of snow. I got tired of watching that one as a kid. You point it towards Washington. Get another snowy channel with a cartoon on it. Now you probably see these used, I think I've seen some of these used for the digital broadcast signals. it'll be mounted like on top of the little stand that you could put on your TV as like an external booster antenna.